Imagine standing on a planet where it rains molten glass sideways at thousands of miles per hour. The sky's a glowing furnace, the ground is a boiling ocean of rock, and the wind is fast enough to strip a spacecraft to metal shavings. Tonight, we're going to step onto worlds that feel less like planets, and more like broken rules of physics. These are exoplanets that, by every comfortable standard taught in textbooks, should not exist. For most of modern history, the solar system was the template. One star, a few rocky planets close in, giant planets farther out on polite nearly circular orbits, orderly, predictable, safe. Then, in just a few decades, that picture shattered. Before we get started, consider the timescale. A generation ago, no one had seen a single planet beyond the Sun. Detection methods were experimental, fragile, barely sensitive enough to pick up the tiniest wobble in a star. Now, in less than one human lifetime, scientists have discovered thousands of worlds across the galaxy, one dim flicker and tiny gravitational tug at a time. Against a background of hundreds of billions of stars, that is the first rough sketch of a new cosmic map. And the map is not neat. It is chaotic. It is wild. Ultra-hot Jupiters skim so close to their stars that their atmospheres are being ripped away by stellar wind. Rogue planets like Ogle, 2016 BLG 1928, drift alone in interstellar space with no sunrise, no orbit, just endless night. Super-Earths hug their stars on orbits shorter than a single Earth day, their surfaces likely drowning in lava oceans. Textbooks once showed planetary systems as tidy families that looked like ours. The reality discovered by modern missions and ground telescopes is closer to a cosmic scrapyard of extremes. There are diamond worlds like 55 Cancri E, where a carbon-rich interior may be squeezed into exotic crystal under unimaginable pressure. There are tidally locked giants like WASP 76b, where vaporized iron may condense and fall as iron rain on the night side. There are tightly packed systems like TRAPPIST-1, where 7 Earth-sized planets crowd closer to their star than Mercury is to the Sun, twisting each other with tides and heat. No one predicts this kind of diversity from the simple diagrams many grew up with. No one expects planets hotter than some stars. Absolutely no one anticipates entire worlds flung free of any solar system at all. Yet the data keep arriving, and with every new orbit measured, the old boundaries of what a planet should be grow thinner. Here is the bold claim. Some of these worlds are so extreme they force scientists to rethink the very definition of a planet. By the end of tonight, you're going to understand why our own solar system might actually be the weird one, and why those sideways glass storms, iron rains, and lonely wanderers in the dark are not just curiosities. They are clues. Clues to how planets form, clues to how they die, and clues that, in the most bizarre corners of space, nature is running experiments no one ever thought to imagine. Now, let's begin. Before we get started with glass storms and diamond worlds, there's a quiet confession to make. For most of the 20th century, scientists assumed the rest of space looked reassuringly familiar. One solar system, one layout, one template. Small rocky planets huddled close to the star. Big gas giants pushed far beyond the frost line, orbits nearly circular, gently nested like clockwork gears. That pattern around the Sun became the pattern for every model. With a sample size of 1, textbooks turned our home into the standard, and everything else into a presumed copy. The logic is simple. Disks of gas and dust form around young stars. Ice survives only in the colder outer regions, so that's where giant planets should grow. Inner regions stay hotter, favouring compact rocky worlds. The result on paper is a calm, stratified system like ours, with circular paths and long, comfortable years. No one expects Jupiter-hugging giants. No one predicts worlds racing around their stars in hours. Then the 1990s arrived, and the universe started arguing back. The first confirmed exoplanets were not found around a sun-like star at all, but around a pulsar, a dead stellar core spinning like a lighthouse and blasting intense radiation. In 1992, planets were discovered circling PSR B Tels 57+12, a place where theory said no stable world should survive. Planetary systems were supposed to die when their stars exploded. These planets were either survivors of cosmic catastrophe or second-generation worlds rebuilt from the wreckage. Both options broke the rules. 3 years later, in 1995, came 51 Pegasi b, the first planet discovered around a sun-like star. It was a Jupiter mass world whipping around its star every 4 days, closer in than Mercury is to the Sun. A hot Jupiter, massive, scorching, hugging the stellar boundary where only small rocky planets were supposed to exist. Prediction versus observation. The models lost. From that moment, everything accelerated. The more the mission teams looked, the stranger the planets became. Gas giants skimming their stars with years shorter than an Earth day. Worlds like WASP-76b and Kelt 9b, with day sides hot enough to vaporize metals and drive supersonic winds from day to night. Planets with such extreme temperature splits that one hemisphere glows while the other freezes in perpetual darkness. And beyond even that, rogue planets like Ogle 2016 BLG 1928, drifting through interstellar space with no star at all. Tonight, we're going to organize this chaos. By the end of tonight, you're going to understand 7 major families of bizarre exoplanets and the specific discoveries that force scientists to rewrite how planets form, migrate, and survive. Hot Jupiters that should never have ended up so close to their stars, ultra-short period worlds with orbits measured in hours, tidally locked infernos with iron and glass rains, super-Earths and lava oceans, rogue wanderers in the dark, and more. Hidden in these anomalies is a deeper pattern, a pattern that hints at how rare solar systems like ours might be, and whether Earth is an exception, or just one quiet outcome in a far wilder cosmic experiment. To see that pattern, the journey has to start with the first truly impossible worlds we found. Those impossible worlds are not just trivia. They say something about you. You are still here, deep into a long-form journey through space, following glass rain, rogue planets, and molten horizons. That means you are part of a very particular group, people who want to understand the universe at more than headline depth. Most viewers tap out after a thumbnail and a title. You stayed for the boundary-pushing details, WASP-76b's iron vapor in the wind, 55 Cancri's potential diamond interior, rogue worlds drifting beyond any solar system. That patience is rare, and it is exactly who this channel is built for. Tonight, we're going to treat these planets the way mission scientists treat raw data. Not as random curiosities, but as clues. Each bizarre orbit, each shattered atmosphere, each lava ocean is a data point in a much bigger experiment about how planets form, migrate, and sometimes get flung into the dark. By the end of tonight, you're going to understand not just which worlds are strange, but why their strangeness matters. That is the mission here. To unpack complex cutting-edge discoveries in a way that feels like sitting on the science team, watching the plots update in real time. When scientists see a tiny dip in a star's light, or a wobble in its motion, or a brief gravitational lensing spike, they are not just ticking boxes. They are arguing, recalibrating, rerunning models, trying to decide whether a new planet has just been discovered or a detector has misbehaved. The goal is to bring you into that process, to slow down enough to show why a transit depth of less than 1% can reveal an ultra-hot Jupiter, why a few meters per second of stellar wobble can betray an invisible super-Earth, why a one-time microlensing flare might be the only sign a rogue planet ever gives. Before we get started with the next phase of this journey, a quick request. If this long-haul dive into strange planets is the kind of space exploration you want more of, take a moment to like this video and subscribe. It is a small click on your side, but it genuinely changes what is possible here. The more engagement a video like this has, the more the algorithm surfaces it to other curious minds who will actually watch past the first minute. No one expects a detailed episode on transit curves or radial velocity signals to reach a wide audience. No one predicts that microlensing or direct imaging will ever trend. Yet when enough people like you interact, absolutely no one anticipates how far a deep dive can travel. And there is more coming. Soon, an entire episode will be dedicated to how these nearly invisible planets are detected at all. Transits shaving off fractions of a percent of starlight, the radial velocity tug-of-war between star and planet, rare microlensing alignments that briefly magnify distant suns, and the razor-thin challenge of direct imaging, pulling a dim world out of a star's glare. Now let's begin the next chapter. To see why these bizarre worlds exist, the story has to rewind to the first confirmed exoplanets, when the idea of planets beyond our solar system still sounded speculative. From there, the timeline will accelerate. Pulsar planets, hot Jupiters, super-Earths, and then the most extreme systems discovered so far. Each generation of discovery will push the pattern a little further until the strangest planets start to make an unexpected kind of sense. To understand how shocking those first bizarre worlds were, you have to rewind to a time when other planets were almost a thought experiment. Before we get started on hot Jupiters and lava oceans, picture the pre-1990s sky. One solar system, one example, and a quiet assumption that the rest of the galaxy more or less followed that template. Scientists talked about planetary systems, but always in the singular. There was the inner zone of small rocky planets, the outer zone of big gas giants, and beyond that the cold, dark reservoir of comets. That tidy architecture was not just familiar, it was the only data point. When theorists built models of planet formation, they built them to reproduce what they already saw. Those early models focused on a flat, rotating protoplanetary disk of gas and dust around a young star. As the disk cooled, solids condensed, collided, and grew. Closer in, where the heat was intense, only rock and metal could survive. Farther out, beyond a critical distance called the snowline, water and other ices could freeze, making planetary cores that were both larger and more efficient at capturing gas. The prediction was clear: small rocky planets near the star, gas giants like Jupiter and Saturn parked far away. Designed for that one familiar system, the theory fed back into expectation. If planets existed around other stars, they would have distant Jupiters, modest Saturns, and maybe an Earth-like world in a comfortable orbit. No one expects a Jupiter roasting so close to its star that its year is a few days long. No one predicts a Neptune-mass planet spiraling in on a wildly elongated path. Science fiction mirrored this confidence. From classic pulp covers to more careful novels, alien civilizations usually lived on Earth-like planets with Earth-like days in Earth-like orbits. Twin suns might rise or rings might hang overhead, but gravity, temperature, and seasons stayed within a familiar band. Over decades, that imagery quietly set public expectations for what a real exoplanet mission would eventually discover. The technology, though, was nowhere near ready. Detecting a planet means detecting something billions of times fainter than its star, or measuring the star's wobble by a few meters per second. For most of the 20th century, instruments simply could not see that far down. The solar wind, the interstellar medium, even the boundary of the heliosphere were easier to probe than a tiny planet hidden in starlight. So the silence was ambiguous. Maybe planetary systems were rare. Maybe they were common but tidy, with distant giants that hardly tugged on their suns. In that vacuum of data, order felt like the safest bet. Tonight, we're going to step out of that safe universe. By the end of tonight, you're going to understand why the first real detections were so jarring. Not serene Earth twins, but violent seared giants, hugging their stars so tightly they tore the old formation models apart and forced scientists to rewrite how solar systems are built. So when the first real planet around a sun-like star finally appeared in the data, it was supposed to be a quiet confirmation. A neat, familiar world to plug into the old diagrams. Instead, 51 Pegasi b crashed the party. In 1995, two scientists, Michel Mayor and Didier Queloz, were watching the light of a fairly ordinary star in Pegasus. No one expects drama from a star like that. The plan is simple: measure tiny wobbles caused by orbiting planets, build a calm census of distant solar systems, and move on. But the wobble they found was huge, and it repeated every 4 days. Not 12 years like Jupiter's slow trek. 4. That period meant only one thing. The planet was hugging its star at a distance far inside Mercury's orbit. The mass? Roughly Jupiter's. The temperature? Hundreds to more than 1,000 degrees, hot enough to bake any atmosphere, drive fierce winds, and turn the upper layers of the planet into a swollen, heated shroud. 51. Pegasi b was the prototype of a new class. The hot Jupiter. A hot Jupiter is a gas giant with the bulk of Jupiter or more, but slammed in so close to its star that its year can be shorter than a work week. Some whirl around in just 2 or 3 days. Their daysides reach temperatures where molecules break apart, where atmospheres puff up and start bleeding into space, where the boundary between planet and star feels disturbingly thin. Contrast that with the solar system you know. Here, gas giants live far out, beyond the icy line where water freezes and solid grains can build massive cores. Jupiter takes nearly 12 Earth years to circle the Sun. Saturn takes almost 30. The inner region is supposed to be the domain of small rocky planets, not bloated, seared giants. Prediction versus observation could not have been harsher. Before we get started on the really exotic worlds, pause on this. Early detection methods were biased toward the louder signals. Big planets, close in. The radial velocity technique that revealed 51 Pegasi b as most sensitive to heavy companions yanking their stars around quickly. Transit surveys, watching for dips in starlight, are far more likely to see a huge planet crossing a star every few days than a small Earth crossing once a year. So the first wave of discoveries was dominated by these monsters. Their existence forced a rewrite of planet formation theory. By the end of tonight, you're going to understand why that rewrite still isn't finished. No one predicts giant planets forming in the furnace next to a star. The only way to make sense of them is migration. In the updated picture, gas giants form far out, in the cold outer disk, then spiral inward through interactions with the gas and dust, carving gaps, trading angular momentum, and sometimes plunging so close they're nearly torn apart, and some keep going. There are hot Jupiters now known with temperatures high enough to vaporize metals, to forge clouds of iron and silicates, to drive alien weather that sounds less like planetary science and more like speculative fiction. Now, let's begin to look at those worlds where it doesn't just rain. It may rain molten glass and condensed metal, and the sky is about to get much stranger than a single misplaced Jupiter. To talk about glass rain and metal clouds with a straight face, you need evidence, not artist impressions, not speculation, real signals pulled out of starlight. Tonight we're going to walk through how scientists see planets that are, in every practical sense, invisible. The core problem is brutal. Planets are small, dark, and lost in the glare of their stars. The original plan is simple. Look for tiny cheats in the light and motion of those stars, and let gravity do the talking. No one expects a distant hot Jupiter to announce itself directly. It announces itself by what it does to its sun. The first big breakthrough comes from radial velocity, the star wobble method. A planet and its star orbit a common center of mass, so the star actually moves, just a little, toward and away from us. That motion shifts the star's spectrum by a few meters per second, the way a passing siren shifts pitch. For the earliest exoplanets, massive gas giants parked scorchingly close in, the wobble was large and fast. Days-long orbits, huge gravitational tugs. This method is exquisitely sensitive to those heavy, close-in planets, which is why hot Jupiters were discovered first, long before gentle Earth-sized worlds. Then comes the pattern interrupt, not motion, but light itself. Transit photometry watches for a planet crossing in front of its star, shaving off a tiny fraction of the star's brightness. Missions like Kepler and TESS stare at hundreds of thousands of stars, looking for dips of less than 1%. Sometimes less than 1/10 of 1%. A planet like Jupiter blocks about 1% of a Sun-like star. An Earth blocks about 1 part in 10,000. Yet from those faint repeating shadows, scientists extract the planet's size, its orbital period, and whether it hugs the star in a tight blistering loop or cruises farther out where temperatures fall. By the end of tonight, you're going to understand that those dips are not just silhouettes. During a transit, a thin ring of starlight filters through the planet's atmosphere. Split that light into a spectrum and fingerprints appear. Sodium lines, water vapor, even vaporized metals in the most extreme systems. That is how worlds like WASP 76b reveal hints of iron in their skies, and how ultra-hot Jupiters advertise that their atmospheres are being stripped and sculpted by stellar wind. There are other, rarer tricks. Gravitational microlensing uses a foreground planet star system as a natural magnifying glass, briefly brightening a background star and exposing planets that drift far from their suns, even near the boundary of interstellar space. Direct imaging pushes spacecraft and telescopes to block a star's glare so that a few young, hot planets can be seen as faint points of light. No one predicts these methods will be easy, yet from wobbles, dimmings, and split spectra, entire alien systems emerge with surprising confidence, setting the stage for the strangest weather forecast in the galaxy. Now, let's begin. The strangest weather forecast begins with heat. Not the gentle warmth of a summer day, but temperatures so extreme they rival the surfaces of small stars. Tonight, we're going to step onto the blast furnace worlds known as ultra-hot Jupiters. These are the overachievers of the hot Jupiter family. Gas giants parked so close to their stars that their daysides soar above 2,000 to even 4,000 degrees Celsius. At those temperatures, familiar chemistry fails. Molecules do not merely warm up, they are ripped apart. Hydrogen, water, methane, even carbon monoxide are shredded into individual atoms, turning the upper atmosphere into a glowing, electrically charged plasma that looks less like a planet and more like the outer layers of a star. Their orbits are tight, often just a few stellar radii from the star's surface. The result is tidal locking, where one hemisphere forever faces the star while the other is plunged into eternal night. Expectation, a simple hot side and a cold side. Reality, a world driven by a colossal imbalance, with temperature contrasts of more than 1,000 degrees and supersonic winds trying and failing to even things out. Those winds are not gentle breezes, they're global jet streams racing from day to night at thousands of kilometers per hour, hauling atoms of hydrogen, oxygen and metals across the planetary terminator. The boundary between blazing day and frigid night becomes a shock zone, a ring of continuous atmospheric violence where space, radiation and chemistry all collide. At these temperatures, even metals surrender. Iron and titanium, which on Earth sit quietly in rocks and ores, can vaporize into the air. The result is a seething metallic haze, a planetary atmosphere laced with iron vapor and titanium oxide, making the whole system feel less like a gas giant and more like an industrial furnace orbiting in space. But the star is not just heating these planets. It is stripping them. Ultra-hot Jupiters sit inside intense stellar winds and ultraviolet radiation fields. Their upper atmospheres swell, escape, and are blown backward, forming comet-like tails that stretch for millions of kilometers. For scientists, these escaping envelopes are a natural laboratory, revealing how atmospheres respond when the normal rules are pushed well beyond their limits. Prediction: a gas giant should be stable and self-contained. Observation: its atmosphere is pouring off into space. By the end of tonight, you're going to understand why these planets may not survive for billions of years, and how their slow evaporation helps map the true boundary between star and planet. No one expects weather to survive in such extremes, yet on some ultra-hot Jupiters, the very metals that vaporize on the day side may cool, condense and fall as rain on the night side. WASP-76b and KELT-9b are the poster children for this regime, where iron clouds, metal winds and night-side condensation hint at literal iron rain. Absolutely no one anticipates that the next local forecast will involve molten metal. Before we get started with those case studies, remember this: ultra-hot Jupiters are not outliers. They are signposts, pointing toward a universe where planets can be as fierce as stars and where weather needs an entirely new definition. Now let's begin with the poster child of metal weather. WASP-76b is not just another hot gas giant in some distant catalogue. It is a world so extreme that scientists genuinely talk about iron rain as part of its forecast. This planet orbits its star in about 1.8 Earth days. 1 year, wrapped up in a long weekend. It hugs its star so closely that its dayside temperature soars to well over 2,000 degrees Celsius, hot enough to vaporize metals that would be solid iron bars in your garage on Earth. The catch is that WASP-76b is tidally locked. One hemisphere faces the star in permanent daylight, while the opposite hemisphere is trapped in endless night. That contrast defines everything. The dayside is a roaring furnace, blasted by stellar radiation and whipped by supersonic wind. The night side is cooler, but only by the standards of ultra-hot Jupiters, still thousands of degrees, yet just low enough that some metals can condense instead of remaining gas. This permanent day-night boundary becomes a laboratory for physics pushed to the edge. Tonight we're going to track what happens to iron as it moves across that boundary. Astronomers cannot fly a spacecraft into WASP-76b's atmosphere, but they can watch starlight filter through it during transits. Using high-resolution spectroscopy, they split that light into thousands of wavelengths, searching for the delicate fingerprints of atoms and molecules in the planet's skies. On WASP-76b, those fingerprints told a very specific story. When the evening limb of the planet, the region where the blazing day side is rotating into night, crossed the face of the star, scientists detected clear signatures of vaporized iron. But on the corresponding morning limb, where the night side rotates back into day, those iron signatures were missing. Prediction versus observation lined up in a single orbit. The best explanation is a brutal metal cycle. On the day side, iron exists as a high-temperature gas, mixed into the atmosphere like steam. Fierce winds drive this iron vapor toward the night side. As it crosses into darkness and temperatures drop, the iron can condense into liquid droplets, potentially forming clouds and then falling out as rain. Not water, but molten metal, plunging through a superheated sky. No one expects telescopes to literally image gleaming raindrops. The evidence comes from those changing spectral fingerprints, from the way the iron signal appears and disappears around the limb. Yet the pattern is so consistent that WASP 76b has become one of the most dramatic case studies of exotic exoplanet weather anywhere in the known solar neighborhood and beyond. By the end of tonight, you're going to understand that this is not just a curiosity. It is a new regime of climate. Imagine just for a moment standing in an indestructible suit under a sky where glowing metal condenses out of the air and falls in sheets. Then ask, if this is what happens where metals survive, what kind of world comes next when even molecules are torn apart by heat no one predicts and absolutely no one anticipates? Now, let's begin with the planet that almost stops being a planet at all. Kelt 9b is where the rules of planetary physics go to burn. This ultra-hot Jupiter orbits so close to its star that its dayside temperature soars above 4,000 degrees Celsius. That is hotter than some red dwarf stars. Hotter than stellar embers that fuse hydrogen in quiet, dim nuclear fires. It sits right on the boundary between a gas giant and a failed star that never quite ignited. The expectation is simple. Planets are cool, stars are hot, and there is a clean divide between them. The reality around Kelt 9 shreds that neat picture. Kelt 9 itself is a massive blue-white star, far hotter and more luminous than the Sun. Kelt 9b whips around it at a distance barely 3 times the star's radius, completing an orbit in about a day and a half. From that vantage point, the star is an enormous blazing disk, filling a huge slice of the sky and flooding the planet with radiation. And not just heat. The star's ultraviolet output is brutal. It bathes Kelt 9b in high-energy photons that slam into the upper atmosphere, break molecular bonds and drive a fierce outflow into space. Scientists see clear signatures that the planet's atmosphere is puffed up and bleeding away, forming a comet-like tail that stretches beyond the planet's gravitational comfort zone. The solar wind there is not gentle. It is a scouring gale. On the day side, the chemistry itself breaks. At a few thousand degrees, even robust molecules cannot survive. Observations show that instead of familiar molecular hydrogen and water, the atmosphere is dominated by individual atoms. Hydrogen, iron, titanium, and other metals stripped out into a thin, incandescent gas. In many ways, Kelt 9b's dayside looks less like a typical planetary sky and more like a stellar photosphere, the glowing surface layer of a star. Tonight, we're going to treat Kelt 9b as a natural laboratory. By the end of tonight, you're going to understand how this one world lets scientists watch atmospheric escape in real time. The planet is literally evaporating. Every orbit, stellar radiation and wind peel off more material, lifting it to high altitudes and then flinging it into interplanetary space. No one expects a gas giant to be permanent at this distance. Over millions of years, Kelt 9b may shrink, transform, or even leave behind a dense, stripped core. Pattern interrupt. This is not just an extreme weather report. It is a warning that the traditional categories, rocky planet, gas giant, star, are not enough. If planets can reach star-like temperatures, can have their atmospheres sculpted, shredded, and boiled away, how many different ways can a world exist? When a planet starts to look like a star, the boundary between them stops being a line and becomes a spectrum, and the rest of the bizarre system still to be discovered may push that spectrum even further. When a planet starts to look like a star, expectations collapse, and then you meet a world that looks, at first glance, like home. A deep, ocean blue marble hanging beside an alien sun. Tonight we're going to step into the atmosphere of HD 1897333b and that calm blue turns into one of the most violent environments ever discovered in space. From a distance, HD 89D733b looks deceptively familiar. It orbits a star about 64 light-years from the solar system, and in early images its rich blue color triggered a reflex in the human brain. Water, sky, something serene, expectation, reality. It is a hot Jupiter, a gas giant so close to its star that its year is just over 2 Earth days. With a blue produced not by oceans but by a hostile atmosphere that scatters blue light while it tears itself apart. Temperatures on the day side climb to around 1000 degrees Celsius. That is hot enough to melt many metals, and it drives a global engine of wind. Models and measurements suggest winds screaming around the planet at several thousand miles per hour. A supersonic conveyor belt hauling heat from the star-blasted dayside into the permanent night. No gentle jet stream. A continuous, planet-encircling storm where day and night are locked in a violent exchange of energy. Inside that storm, the chemistry becomes strange. Spectra taken by space telescopes show signatures that match tiny silicate particles suspended high in the atmosphere. Under the right pressures and temperatures, those silicates can condense into droplets. Not raindrops of water, but molten glass. Imagine a cloud deck where droplets of liquid rock form, grow, and then fall, not straight down but sideways, driven horizontally by winds that outrun a rifle bullet. No one predicts glass rain when drawing the first sketches of a distant planet, yet the evidence keeps pointing in that direction. Astronomers split the planet's light into spectra and compare the fingerprints of its atmosphere with models of different cloud compositions. Silicate hazes explain the blue color. High-temperature cloud models show that if those silicates cool just enough on the night side, they should condense and fall. It is a chain of inference, not a direct image, which is why scientists are careful. The glass rain scenario fits what has been discovered so far, but the exact particle sizes, cloud heights and wind patterns remain an active frontier. By the end of tonight, you're going to understand that this is not just a curiosity. Worlds like HD 89D733b redraw the boundary of what weather can mean. Picture an endless midnight sky lit by a nearby star, a horizon where the atmosphere glows, and a storm of glass racing sideways around the planet. And then remember, not all bizarre worlds are swollen gas giants. Some are rocky, close-in planets where the atmosphere is thin or gone, and the entire surface is not an ocean of water but a global sea of lava, glowing red beneath the same unforgiving physics. So now leave the glass storms of the hot Jupiters behind and drop down towards something even more unsettling. A world where the ground is not solid land, but a churning, glowing sea. Not an ocean of water, an ocean of rock. These are lava worlds. Rocky exoplanets pressed so close to their stars that their surfaces are partially or even entirely molten, trading mountains and continents for global magma oceans that flow like a planetary-scale foundry. In our solar system, Mercury brushes this regime and Io flirts with it through tidal heating. But these planets go far beyond, locked in orbits so tight that the concept of a stable crust becomes almost optional. The orbits are the first shock. Some of these worlds circle their stars in less than a day. One sunrise, one sunset, and the year is already over. At those distances, the incoming stellar radiation is not just a little higher than Earth's. It can be hundreds of times more intense, driving surface temperatures to well above the melting point of silicate rock, past the threshold where granite, basalt, and iron-bearing minerals simply surrender and liquefy. Prediction meets observation here in a way that forces scientists to rethink how rocky planets behave. Models long suggested that young terrestrial planets pass through a molten phase, with global magma oceans slowly cooling, outgassing, and solidifying. Lava worlds are like a time machine, freezing that early stage in place. They offer a living laboratory for the violent youth of Earth, Venus, and Mars. When the solar wind raged, impacts were constant, and the boundary between rock and atmosphere was blurred by heat. On some of these planets, that blur becomes literal. Temperatures climb so high that the surface does not just melt, it starts to evaporate. Rock turns to vapor. Elements such as sodium, calcium, magnesium, even silicon can be lofted off the magma ocean, forming a thin, exotic atmosphere that would look nothing like the familiar blue dome above Earth. Tonight, We're going to treat those atmospheres as clues, because when starlight filters through them, it carries spectral fingerprints that reveal what is boiling off the surface. No one expects a rocky planet to behave like a comet, shedding its own crust into space, yet that is exactly what these observations imply. By the end of tonight, you're going to understand why some teams describe these worlds as evaporating Earths, slowly losing mass as the star's radiation strips away vaporized minerals and drives planetary evolution in real time. Now let's begin to push deeper beneath the lava and the rock vapor into the interiors. Around certain carbon-rich stars, the chemistry flips. Carbon can dominate over oxygen, changing what minerals crystallize as a molten planet cools under immense pressure. In those conditions, carbon is not just a trace impurity, it can reorganize into diamond, potentially on colossal scales far beyond anything in Earth's mantle. No one predicts entire mantles rich in diamond, yet some simulations of worlds like 55 Cancri E point in exactly that direction. A planet with a year shorter than an Earth day, a surface of lava, an atmosphere of rock vapor, and an interior where carbon may lock into vast, glittering structures. And just when that sounds like the most extreme configuration possible, the next set of observations will suggest something even stranger, hiding on its night side. The picture that emerges from those simulations is almost unbelievable. A world so close to its star that a full year races by in less than 18 hours. A super-Earth, called 55 Cancri E, with about twice Earth's radius and several times its mass, whipped around its sun-like star at a distance so tight that it's likely tidally locked and roasted from one side forever. Now, let's begin. When a planet orbits this close, the rules change. The day side is blasted by intense radiation, the night side is plunged into permanent darkness, and the entire surface becomes a laboratory for extreme physics. Observations from space telescopes show temperatures on 55 Cancri's dayside soaring above 2,000 degrees Celsius. That is hot enough to melt many rocks. Scientists suspect the dayside may not be a solid landscape at all, but a rolling incandescent magma ocean. Its density adds another twist. For a planet this size, 55 Cancri is too compact to match Earth's familiar mix of iron core and silicate mantle. The numbers hint at an interior with a different recipe, more carbon, less oxygen, a chemistry that pushes it into a regime almost no one expects for a rocky world. This is where the carbon world hypothesis comes in. If 55 Cancri formed in a region of its solar system where carbon was abundant and oxygen relatively scarce, its rocks would not mirror Earth's granite and basalt. Under immense pressure deep inside, carbon atoms could lock together into ultra-hard phases. Over geologic timescales, layer by layer, those phases might crystallize into diamond. Tonight, we're going to lean into that image for a moment. Not a single planet-sized jewel hanging in space, but something stranger. Imagine a mantle built from carbides and exotic minerals, threaded with thick horizons of diamond, capped by a surface where lava rivers glow red-white under a black sky. By the end of tonight, you're going to understand why Diamond Planet is both accurate in spirit and misleading in detail. Because the reality, as far as current models can reach, is messy. The interior would be a complex mixture of silicon carbide, iron carbides, compressed silicates, and perhaps stacked diamond layers, all jostling under crushing gravity. The surface might exhale an atmosphere made from vaporized rock and carbon-bearing gases that shift with the stellar wind. And the night side. Some data hint at hotspots, storms of molten rock, or even pools where that magma briefly cools and remelts. Here's the pattern interrupt. For all the dramatic headlines, scientists are still arguing over the basic ingredients. Different measurements of its heat, its possible atmosphere, and its star's composition pull in competing directions. No one predicts a simple answer, and absolutely no one anticipates that 55 Cancri will fit neatly into Earth-based categories. What it does, instead, is stretch the imagination about what a rocky planet can be. It shows that, beyond our solar system, Earth-like can mean lava oceans, carbon mantles, and buried diamonds. And just when that sounds like the outer limit of planetary weirdness, the next destination breaks another boundary. Worlds that are not bound to any star at all, drifting alone through interstellar space with no sunrise and no sunset, just endless night. If 55 Cancri hints at buried diamonds, carbon worlds push that idea to the limit. They suggest entire planets where geology, weather, and even the definition of rock are rewritten from the ground up. Now, let's begin with the star itself. When a star and its protoplanetary disk form, the mix of elements in that disk sets the rules for every planet that follows. Change the carbon to oxygen ratio, and you change the menu. Around stars with more oxygen than carbon, silicates dominate, and worlds like Earth emerge. Mantles of olivine and pyroxene, crusts of basalt and granite, familiar volcanic arcs and plate tectonics. Tilt that ratio toward carbon, and the chemistry flips. Suddenly, instead of silicate minerals locking up most of the elements, carbides and carbon compounds take over. In those disks, planets can condense as true carbon worlds. Their mantles might be packed with silicon carbide and titanium carbide, sheathed in thick layers of graphite, with pressures at depth squeezing carbon into diamond shells hundreds of kilometers thick. Imagine a planet where the upper crust is dark, metallic-looking carbide, the mid-layers are lubricating graphite, and the deep interior is a glittering, super-hard diamond lattice. The familiar rules of plate tectonics break. Graphite is weak and slippery, diamond is incredibly strong, and that contrast could produce strange fracture zones, episodic quakes, and volcanic eruptions that bleed carbon-rich magmas instead of silica-rich lavas. Tonight, we're going to lean into that alien geology. On Earth, volcanoes outgas water vapor, carbon dioxide, sulfur, building an atmosphere that can support liquid oceans. On a carbon planet, those same deep processes might vent methane, acetylene, carbon monoxide, and long-chain hydrocarbons. The sky could be hazy orange or inky black, thick with smog-like aerosols. Rain might not be water at all, but hydrocarbons condensing and evaporating in a cycle more like Titan's than Earth's, only hotter, denser, and more chemically aggressive. Surface rivers could be liquid organics flowing over graphite plains, carving channels into a crust that conducts electricity better than many metals. By the end of tonight, you're going to understand why scientists are suddenly obsessed with stellar chemistry. No one expects a small change in the carbon-to-oxygen ratio to rewrite entire planets, but that is exactly what models now suggest. No one predicts that two stars with the same mass and age but slightly different elemental mixes could host one system of blue oceans and green continents and another of black carbides and diamond mantles, and absolutely no one anticipates how diverse those atmospheres will look once spectra can be captured in detail. Before we get started on rogue worlds and planets without suns, there is a boundary being crossed in real time. Telescopes like the James Webb Space Telescope are already sniffing the atmospheres of super-Earths and mini-Neptunes, searching for carbon monoxide, methane, and exotic hazes that betray carbon-rich formation histories. Future missions will push this farther, turning faint spectral lines into full climate and geology models. So here is the question. If an indestructible suit were waiting on a landing craft, would you walk across a graphite plain under a hydrocarbon sky, lightning flickering through organic smog, or descend toward the crushing hot depths where diamond forms and the planet's carbon heart grinds and flexes in the dark? Most bizarre of all, you might choose neither the carbon storm nor the diamond depths. You might step off the ladder into something even stranger, a world with no sunrise at all. Tonight, we're going to leave stars behind and follow the planets that travel through space alone. These are rogue planets, also called free-floating planets. They do not orbit a sun, or any star or anything at all except the galaxy's center of mass. Some may have formed in isolation, collapsing directly from clumps in the interstellar medium. Others were born in ordinary solar systems and then violently evicted, flung away by gravitational encounters with giant planets, passing stars, or the slow chaos of crowded orbits. The expectation is that planets stay in their lanes. The reality is that gravity throws some of them out. Imagine standing on the surface of one of these worlds. There is no dawn, no blue sky, no solar glare creeping over a horizon. Above, only a dome of distant, unblinking stars frozen in their patterns for millions of years because your planet no longer has a day-night cycle tied to a parent star. The ground under your boots would be unimaginably cold, hundreds of degrees below freezing, the air, if there is any, locked in nitrogen or methane ice. And yet, deep below, radioactive elements and residual formation heat could keep an interior ocean faintly warm, glowing only in infrared, a hidden sea under an eternal night. For scientists, these planets are nearly invisible. They do not reflect a nearby star's light. They do not transit across a bright disk. They do not blaze in infrared the way hot Jupiters do. So how are they discovered at all? The answer is gravity itself. When a rogue planet drifts in front of a more distant background star, its gravity bends and focuses that star's light. For a few hours or days, the star brightens in a precise, symmetric way. Then the effect vanishes. This is gravitational microlensing, and it turns otherwise undetectable planets into brief, perfect natural telescopes. One event, Ogle 2016 BLG 1928, pushed this technique to its limit. The brightening lasted just over 40 minutes, one of the shortest microlensing events ever recorded. Models showed a lens with about Earth's mass, with no detectable host star. No one expects a full planet to reveal itself in less time than a lunch break. No one predicts that a single spike in a light curve can prove an entire world is drifting between the stars, and absolutely no one anticipates how many more may be hiding. Because if short, rare flashes like this are already turning up in modest surveys, then there may be billions of rogue planets in the Milky Way, perhaps more orphaned worlds than stars themselves, filling the dark between systems like invisible shrapnel from planetary formation. By the end of tonight, you're going to understand that solar system is only one way for planets to live. The next question is obvious. If a planet can survive without a sun, what else can survive out there with it? So picture one of those orphaned worlds again. No sunrise, no sunset, just a black sky and a frozen surface racing through interstellar space. By every instinct, this looks dead. Yet some scientists argue that under the ice, under the rock, a rogue planet might be more alive than it appears. The expectation is simple. No star, no light, no heat, no life. The reality could be stranger. A massive planet with a thick atmosphere rich in hydrogen or carbon dioxide could trap its own internal heat, turning that atmosphere into a giant thermal blanket. Radioactive elements in the interior keep decaying, residual heat from formation keeps leaking out, and the greenhouse effect keeps that energy from escaping too quickly into space. Now, let's begin with the most important ingredient, liquid water. On the surface, a rogue world would be brutally cold, with temperatures hundreds of degrees below freezing and a thin, ghostly glow from distant stars at best. But drill down and the picture changes. A deep ocean buried beneath kilometers of ice could sit on top of a rocky mantle warmed from within. It would be dark, high pressure, and slow. Yet in principle, it could remain liquid for billions of years. Before we get started on how weird that is, compare it to something closer to home. Europa and Enceladus circle Jupiter and Saturn inside our own solar system, far from the warm inner regions where Earth orbits. Their surfaces are frozen, but spacecraft have detected evidence of subsurface oceans, plumes of water vapor, and complex chemistry. There, tidal heating from their giant planets flexes and kneads their interiors, generating heat without sunlight. That is the pattern interrupt. Life in the solar system might not cling to the sunlit surface at all. It might huddle around vents at the bottom of hidden seas, powered by geology rather than light. Replace tidal heating with radioactive decay, stretch the scene out into interstellar space, and a rogue planet becomes an unlit cousin of Europa or Enceladus. No one expects a starless world to host anything but frozen rock. No one predicts a planet drifting beyond every visible boundary of a solar system could keep an ocean quietly simmering under ice. Yet the physics does not forbid it. Chemistry in those warm, high-pressure depths would proceed slowly but relentlessly, with gradients of temperature and minerals acting as energy sources. Over immense timescales, slow is not a problem. Slow is an opportunity. The catch is that these planets are almost invisible. Many rogue worlds are only discovered when their gravity briefly lenses the light of a background star, a fleeting blink in the galactic wind. Detecting a thin atmosphere is hard. Detecting an underground ocean is harder. Detecting life beneath that ocean from dozens or hundreds of light years away is, for now, beyond any mission or spacecraft on the drawing board. So for the moment, rogue biospheres are mostly thought experiments, but they do something profound. They force a rewrite of what habitable zone means. If a planet without a star might sustain liquid water, then habitability is not just a ring around a sun, it is a property of planets themselves. By the end of tonight, you're going to understand why that matters, because some planets sitting comfortably inside classic habitable zones are among the strangest, most hostile worlds ever discovered. So if habitability is not just a ring around a star, what is it? In classical terms, the habitable zone is simple. It is the range of distances where an Earth-like planet, with an Earth-like atmosphere, could keep liquid water on its surface. Too close and water boils away, too far and it freezes solid. That picture is clean. It is also wrong in almost every interesting case, because what really controls a planet's climate is not just how far it sits from its sun, but how it traps, reflects, and redistributes energy. Change the atmosphere, and you move the boundary. Add more greenhouse gases, and a world can stay warm far beyond the textbook habitable zone. Strip the air away or cover the planet in bright reflective clouds, and even a close-in world can end up surprisingly cool. Tonight, we're going to stretch that idea until it almost snaps. Atmospheric composition, greenhouse gas levels, global cloud decks, even how fast a planet spins, all act like dials that scientists can turn in their models. Slow the rotation and heat lingers on the day side. Speed it up and winds whip energy around the globe. A denser atmosphere can carry warmth from a star-facing hemisphere into permanent night. A thinner one can let heat leak into space, turning a seemingly safe orbit into an icebox. This becomes critical around red dwarfs. These small, cool stars dominate our galaxy, and their habitable zones hug close in. Close enough that tidal forces grab onto planets and lock them, the way our moon is locked to Earth. One hemisphere bakes in endless day, the other freezes in perpetual night. At first glance, no one expects such a world to be friendly. But climate simulations reveal something strange. Under the right pressure and composition, winds and circulation can carve out a twilight band, a narrow terminator ring where temperatures hover near the melting point of water. A permanent sunset wrapped all the way around the globe. Oceans, if they exist, could pool there. Clouds could form and rain could fall there, even while the dayside glows and the nightside glitters with ice. By the end of tonight, you're going to understand why that single ring might be more important for life than an entire classical habitable zone. Once that possibility is on the table, almost no world is automatically disqualified. Strong tidal forces can flex a planet's interior and power volcanism and subsurface oceans. Unusual compositions from carbon-rich mantles to high metal atmospheres can build exotic climates where chemistry still runs, slowly or quickly. Eccentric orbits can drive wild seasons, but also create windows of temperate conditions that repeat for billions of years. No one predicts exactly where life might take hold in such shifting environments, and absolutely no one anticipates every niche evolution could exploit. Now, let's begin a concrete test of these ideas. The TRAPPIST-1 system is a compact family of 7 Earth-sized planets packed closer to their cool dwarf star than Mercury is to our Sun. Several sit in the nominal habitable zone, yet all of them feel intense tidal stretching, powerful magnetic interactions, and probably fierce stellar winds. On paper, they are prime real estate. In reality, they may be among the strangest potentially habitable planets ever discovered. So when you zoom in on TRAPPIST-1, you're not looking at a normal solar system scaled down. You're looking at a cosmic pocket watch, a tiny, cool red dwarf star, only slightly larger than Jupiter, with 7 Earth-sized planets, all packed closer in than Mercury is to our Sun, all moving in a pattern so precise it feels engineered. Tonight, we're going to stand inside that pattern for a moment. TRAPPIST-1's star glows a dull, deep red, putting out a fraction of the light you're used to, but its planets huddle right up against it. Their orbits are so compact that, from one world, the neighbouring planet could loom larger than our moon in the sky. Transit after transit, shadow after shadow, the whole system ticks along like gears in motion. This is where orbital resonance takes over. Now, let's begin. In simple terms, resonance means the planet's years come in neat ratios. While one completes, say, 6 orbits, another might complete 9, and another 12. Every time those alignments repeat, their gravity gives each neighbour a tiny tug, like a metronome nudging another metronome back into rhythm. Over millions of years, those regular pulls lock the configuration into a delicate clockwork-like chain. No one expects such tight packing to be gentle. With orbits this close, the star's gravity doesn't just hold these planets. It needs them. They flex as they move, stretching and relaxing with every lap. That flexing turns orbital energy into heat. The same tidal forces that power volcanic Io in our own system could be far stronger here, driving relentless geological activity, deep tidal heating, perhaps even global subsurface oceans on some worlds, and vast lava fields on others. TRAPPIST-1 is not just a dynamical showpiece. At least 3 of its planets sit in the star's habitable zone, where starlight is, on paper, gentle enough for liquid water on a surface. By the end of tonight, you're going to understand why that phrase, habitable zone, can be misleading. These worlds are prime targets for the James Webb Space Telescope and future spacecraft. Perfect laboratories to search for atmospheres, clouds, maybe even hints of chemistry pushed far beyond Earth's experience. But even Earth-sized does not mean Earth-like. Bathed in red light, many of these planets are probably tidally locked, with one hemisphere in eternal day and the other in endless night. Winds could scream around the terminator line, shuttling heat from a scorching day side to a frozen dark side, creating climates that defy familiar ideas of seasons and weather. And if TRAPPIST-1 can hide 7 such worlds in a volume smaller than Mercury's orbit, what might be hiding around hotter, harsher stars, where resonance, tides, and stellar wind push planets to even more extreme fates? Those winds don't just shape orbits. They can lock entire worlds into a strange, perpetual pose. Now, let's begin with one of the most alien arrangements a planet can have: tidal locking. When a world orbits very close to its star, gravity doesn't just pull. It squeezes, flexes, and drags on the planet's interior until its rotation slows and finally matches its year. One spin equals one orbit. One hemisphere stares at the star forever. The other is plunged into endless night. The expectation is simple: dayside, a scorching furnace, blasted by unending radiation. Nightside, a frozen wasteland so cold even the atmosphere might collapse as gases turn to ice. No one predicts a place like that could be stable, much less habitable. But climate models tell a more complicated story. If the planet has a thick atmosphere, or better yet, deep oceans, winds and currents can transport heat from day to night, softening the contrast between blazing and frozen. By the end of tonight, you're going to understand why some scientists now talk seriously about terminator habitability. On a tidally locked world, there is a permanent ring of twilight, the narrow band where the star forever clings to the horizon. There, the energy balance can land in a sweet spot. Not too hot, not too cold, with temperatures that could allow liquid water to pool, provided the air is dense enough to spread heat and resist freezing on the dark side. Imagine standing in that ring. The star never rises, the star never sets. It just hovers at the horizon, locked in an eternal sunset painting the sky in permanent orange and red. Shadows stretch infinitely long. Winds roar from the blistering dayside toward the frozen night, then curve and shear as planetary rotation and pressure gradients twist them into global jet streams. Oceans, if they exist, could carry warm surface water toward the night and send cold, dense water sliding back along the depths. But this fragile balance sits under a dangerous star. Many tidally locked planets orbit red dwarfs, small suns with violent tempers. Their flares can be hundreds of times more energetic than typical solar eruptions, bathing the planets in high-energy particles. Over billions of years, that bombardment can strip atmospheres, push the habitable boundary inward and outward, and leave bare rock where oceans once were. No one expects a calm sky when the host is young and active. There are other challenges. A world where the star never moves would shape ecosystems and psychology in ways that are hard to imagine. On the day side, organisms would adapt to constant glare and heat. On the night side, life might rely on geothermal energy, chemistry, or faint reflected light from the bright hemisphere. In the twilight ring, circadian rhythms would have to anchor to something other than sunrise and sunset, because those concepts simply do not exist. Pattern interrupt. Not all extreme climates come from locking. Some come from stretching. Push a planet into a highly eccentric orbit, and it doesn't face eternal day and night. Instead, it plunges toward its star, baking in a brief, searing summer, then swings far out, freezing in a long, deep winter. Worlds like this can alternate between molten and frozen in a single year. Tonight, we're going to follow those orbits next, to planets that don't just live in one climate, but swing between extremes that would tear apart any familiar idea of seasons in our own solar system. Now, let's begin. Those plunging paths are not rare exceptions. In deep space, many planets don't move in neat circular tracks like Earth. They race along stretched ellipses. At one end, periapsis, they dive dangerously close to their star. At the other, apopsis, they drift far out into the dark. Same star, same planet, completely different worlds, depending on where it is in its orbit. This is orbital eccentricity. 0 means a perfect circle. Push that number toward 1, and the orbit elongates, like pulling a ring into an oval. For some exoplanets, that oval is extreme. They can swing from a sun-skimming pass, where the stellar wind roars and the atmosphere boils, to a distant cruise where temperatures fall hundreds of degrees. By the end of tonight, you're going to understand why a single year on these planets can feel like moving between a blast furnace and a cryogenic lab. Those temperature swings are not gentle seasons, they are planetary whiplash. Near periapsis, ices can flash directly into vapor, rock can soften, and atmospheres can balloon, driving ferocious winds that try to redistribute all that sudden heat. Then, as the planet climbs back out, gases can condense, clouds can collapse, and even surface materials can refreeze, locking in scars from the last close pass. No one expects stable climates here. These are worlds that inhale and exhale entire atmospheres with every orbit. The star's gravity does more than heat the surface. At close approach, tides dig deep. The near side of the planet is pulled harder than the far side, flexing the interior like a stress ball in slow motion. That constant kneading generates heat, powering volcanism, magma oceans, and in extreme cases, tearing apart loosely bound moons or rings. In our own solar system, Jupiter does this to Io. Around other stars, the effect can be far more violent, because the orbits are more eccentric and the passes are closer. Scientists infer these wild paths from tiny wobbles and timing shifts. Radial velocity measurements show stars speeding up and slowing down in uneven rhythms, betraying planets on elongated orbits. Transit timing variations reveal worlds tugging on each other, arriving early or late in front of their star. Systems like HD 80606b, with a hugely eccentric orbit, look nothing like the nearly circular architecture seen at home, and some close-in giants, like WASP 12b, take this to the limit. Their orbits bring them so near that the star's gravity stretches them into rugby ball shapes, and siphons their atmospheres into space. No one predicts a tidy, long-term future for planets like this. They are being distorted, heated, and slowly consumed. In the next section, the mission goes even closer, to worlds so tight to their stars that their shapes, skies, and even their survival challenge every boundary of what a planet can be. Those worlds are being peeled like onions. But WASP 12b is on another level. This is what happens when a planet doesn't just lose its atmosphere into space, it loses it straight into the jaws of its star. Now, let's begin. WASP 12b is a hot Jupiter, parked so close to its star that its entire year lasts just over a single Earth day. One sunrise, one sunset, and the orbit is complete. It orbits at only a few stellar radii, buried deep inside the star's gravitational grip, where the star's pull on the near side and far side of the planet is dramatically different. Those tidal forces never let up. They stretch the planet, they twist it, they reshape it. From a distance, a normal gas giant is a nearly perfect sphere. WASP 12b is not. Under those relentless tides, its body is pulled into an elongated egg-like shape, pointed toward its star. The same physics that raises ocean tides on Earth and drives volcanic chaos on Io is operating here, but magnified far beyond anything in the solar system. As the planet flexes, its interior is kneaded like dough, converting orbital energy into heat, inflating the atmosphere and likely driving fierce internal winds that race around the planet. By the end of tonight, you're going to understand that this distortion is only the beginning of its problems. Observations in ultraviolet light show that WASP 12b is surrounded by a vast shroud of gas, a swollen envelope that spills beyond the planet's Roche lobe, the gravitational boundary where material can remain bound. No one expects that gas to just hang there. The star's gravity grabs it, pulling it into streams and clouds that arc inward, feeding the star like a slow, planetary drizzle. In effect, the planet is being eaten. Spectra reveals signatures of escaping hydrogen and heavier elements, telling scientists that WASP-12b is actively losing mass. Some estimates suggest it could be shedding billions of tons per year, an invisible comet of gas wrapped around a doomed core. As the mass flows outward from the planet and inward toward the star, angular momentum is exchanged. The orbit shrinks, the period shortens. Each year that lasts a day becomes a little shorter than the last. This is not a stable configuration. Over millions of years, tidal interactions and mass loss will likely drag WASP-12b inward until it is torn apart or fully absorbed, leaving behind only subtle scars in the star's rotation and composition. No one predicts a permanent hot Jupiter here. WASP-12b is a transient phenomenon, caught in the act of transformation, a reminder that some planets are brief episodes in their system's history. Tonight, we're going to follow that logic one step further. If a planet can be stretched, boiled, and consumed, what happens to worlds so hot that their very atoms are stripped, where metals vaporize and fall as rain? The next exoplanets push even this violent picture to the edge. To push that picture to the edge, you return to one of the strangest worlds in the catalogue, a planet so hot that metals don't just melt, they vaporize. Kelt 9b is where planets start to look uncomfortably like stars. Now, let's begin. Kelt 9b orbits a blue-white star hotter than most in our solar neighbourhood, whipping around it in just about a day and a half. The expectation is a normal hot Jupiter, puffy, stressed by tides, but still recognisably a planet. The reality is a world heated to well over 4,000 degrees Celsius on its day side, hotter than some red dwarfs, with gravity stretched and squeezed by tidal forces until its atmosphere is pulled into an elongated, almost teardrop shape. In that furnace, the upper atmosphere does not behave like a typical gas giant. The star's ultraviolet radiation hammers the planet, driving atmospheric escape that looks more like a stellar wind than a gentle leak. Hydrogen, the lightest element, is blasted away first, but it does not leave alone. Heavier atoms hitch a ride. Spectra taken as the planet passes in front of its star reveal the telltale fingerprints of iron, titanium, and other metals. Not locked in clouds or droplets. Individual atoms racing through a superheated envelope at tens of kilometers per second. From a distance, that envelope can resemble the thin, hot, outer layers of a small star, with lines in the spectrum that challenge the neat boundary between planetary and stellar physics. The atmosphere does not end where the solid planet would. It keeps going, inflated and dragged downstream, forming an extended shroud and very likely a comet-like tail of escaping gas. No one expects a gas giant to grow a tail longer than some entire planetary systems. Yet that is what the data suggest, a world in the act of being stripped. Models indicate that over hundreds of millions of years, Kelt 9b could lose a significant fraction of its mass, its outer layers peeled away and fed into space. Here the classification problem becomes more than a naming game. By the end of tonight, you're going to understand why. When a gas giant reaches star-like temperatures, shows metal absorption lines, and drives its own outflow, does it still belong in the same category as Jupiter? Or is it edging toward the regime of brown dwarfs and failed stars, objects that blur the boundary between planet and star in both formation and behaviour? For scientists, those labels track different birth stories, different migration histories, different futures. Pattern interrupt. Kelt 9b is extreme, but it is not alone at the frontier. For every ultra-hot giant shredding itself in plain view, there are super-Earths hugging their stars with lava oceans, mini-Neptunes puffed up by relentless radiation, and compact systems where planets tug on each other in tight gravitational dances. Some may have rocky surfaces and familiar densities, yet hide atmospheres of exotic chemistry and crushing pressure. As the mission to map these worlds continues, each new discovery forces a deeper question. How many ways can a planet exist, and which of those ways might still allow something living to look up at its alien sky? Tonight, we're going to follow that question into even stranger territory, where worlds made of glass, carbon, and perhaps diamond orbit suns far beyond our own system. Those glass and carbon worlds feel alien, but the strangest revelation from this exoplanet census is quieter and closer to home. The galaxy's most common planets are the ones our own solar system simply does not have. These missing worlds sit in an in-between zone, too big to be Earths, too small to be Neptunes. Scientists call the lower-end super-Earths, planets with masses between Earth and Neptune, often only 1.5 to maybe 10 times Earth's mass. Many are probably rocky, or cloaked in relatively thin atmospheres compared to the swollen envelopes of the giant planets. Push just a bit larger, and you cross an invisible boundary into mini-Neptunes. Similar mass range, very different personality. These are worlds with substantial gaseous envelopes, hydrogen and helium, maybe mixed with water vapor and other volatiles, wrapped around rocky or icy cores. Not full-blown gas giants, but not solid ground under your feet either. Now let's begin. When the Kepler mission started counting planets by the thousands, one pattern leapt out. In the radius range between Earth and Neptune, the histogram didn't flatten. It spiked. Super-Earths and mini-Neptunes are everywhere, around cool red dwarfs, around sun-like stars, packed tightly into systems where multiple planets orbit closer than Mercury. By the end of tonight, you're going to understand why that makes our own system look strangely empty. Look around locally. There is Earth, then a long jump to Uranus and Neptune. No intermediate worlds, no super-Earths with double our radius, no mini-Neptunes hovering just below Neptune's size. For decades, textbooks quietly implied that this layout was normal. Kepler shattered that assumption. In statistical terms, our solar system is the oddball. That middle mass range is powerful. With more gravity than Earth, but less than Neptune, these planets can follow many different evolutionary paths. Some may be scaled-up rocky planets with thick mantles and high gravity, where mountains crush under their own weight and atmospheres hug the surface like a heavy blanket. Others may be water-rich worlds, with global oceans hundreds of kilometers deep, high-pressure ice phases forming strange layers beneath black, sunless seas. Still others swell into gas-draped mini-giants, their dense cores buried under hazy, many hundreds kilometers thick atmospheres sculpted by stellar wind and radiation. Then Kepler revealed an even subtler clue, a radius gap. Plot planet size versus frequency, and there is a dip between smaller super-Earths and slightly larger mini-Neptunes. Something is erasing atmospheres right at that scale. No one predicts the details perfectly, but the leading idea is atmospheric loss. Young stars blast their planets with high-energy radiation. Lighter envelopes boil away, leaving bare super-Earths. Heavier ones hang on, staying puffy mini-Neptunes. This single feature, one notch in a graph, means that even within this ordinary category, evolution pushes planets toward very different outcomes. Solid, oceanic, gaseous. 3 destinies carved by mass and starlight, and that forces a hard question. If the most common planets are ones we don't have, how typical is Earth really? Tonight we're going to follow one candidate that feels familiar at first glance, Kepler 452b, a so-called super-Earth cousin in a sun-like star's habitable zone that might be both comfortingly Earth-like and profoundly alien at the same time. On paper, Kepler 452b looks almost boring, a planet going around a star very much like the Sun, at almost the same distance, taking about 385 days to complete a year. If the ultra-hot Jupiters are the rock stars of exoplanet science, this one looks like the quiet cousin in the corner. Now, let's begin. Kepler 452b orbits in what scientists call the habitable zone, the region where liquid water could exist on a rocky surface. The host star is a G-type like our Sun. The orbital distance is close. The year is only a few weeks longer than an Earth year. By the end of tonight, you're going to understand why that superficial similarity made headlines, and why it is also deeply misleading. Because when the numbers are pushed, the differences start to stack up. Kepler 452b is about 60% larger in radius than Earth. That may not sound extreme, but volume scales fast and the planet is likely several times more massive. That extra mass means stronger gravity. Walking on the surface, every step could feel like carrying another person on your back, if it has a solid surface at all. Stronger gravity doesn't just weigh you down, it holds on to more gas. That could mean a thicker, denser atmosphere, with higher surface pressure and a powerful greenhouse effect. The same physics that lets a super-Earth keep its air can also push it toward a Venus-like fate, where the sky turns into a pressure cooker and oceans, if they ever existed, boil away over billions of years. And the clock has been ticking for a very long time. Kepler 452's star is older than the Sun by perhaps 1.5 billion years or more. That extra time is everything. If this planet started with oceans and continents, tectonic plates and active volcanoes, its biosphere, if one ever arose, would have had longer to evolve than life has had on Earth. More time for complexity, more time for collapse. That's where the mission turns from hopeful to haunting. An aging star brightens, its habitable zone creeps outward. A world that was once comfortably temperate can be pushed past a critical boundary into a runaway greenhouse, the way climate models predict for Earth in the distant future. Kepler 452b may be a preview of our own planet's long-term destiny, playing out right now, 1/400 light-years away. But here is the catch. No one expects clarity at this distance. Kepler 452b was discovered by watching its star dim slightly as the planet crossed in front, so its size and orbit are known, but its true composition is not. Rock, water-rich, or mini-Neptune. No one predicts that a single transit curve can tell us whether there is an atmosphere, clouds, or oceans. The Earth 2.0 label is more marketing than measurement. So Kepler 452b sits in a strange category: familiar orbit, Sun-like star, but older, heavier, and possibly already tipping into a greenhouse catastrophe. It shows that even the most normal-looking planets can live in evolutionary contexts that make them far stranger than the nickname suggests. Tonight, we're going to leave this almost Earth behind and dive back into the truly extreme, worlds of glass rain, molten skies, and planets that drift through space with no star at all. If those almost Earths felt uncomfortable, the next class of worlds abandons comfortable completely. Tonight, we're going to drop almost onto the stellar surface itself, to planets that race around their suns in less time than it takes you to get a good night's sleep. These are ultra-short period planets, worlds that whip around their stars in less than one Earth day, sometimes in just a few hours. That orbital period means unimaginable proximity. Instead of sitting at a safe distance like Earth in the solar system, these planets skim along just a few stellar radii above a roiling photosphere, immersed in radiation and tidal forces so intense that many scientists once doubted such orbits could remain stable. Most of the ones discovered so far are super-Earths, or shrunken sub-Neptunes. They may have started as mini-Neptunes, wrapped in thick envelopes of hydrogen and helium, but that close to a star, the stellar wind is a blowtorch. Over hundreds of millions of years, the outer layers are stripped away, molecule by molecule, leaving behind dense rocky cores. What remains is not a quiet terrestrial surface, but a world where rock itself can't stay solid. At these distances, tidal locking is nearly guaranteed. One hemisphere faces the star forever, while the other never sees dawn. On the day side, temperatures can soar above 2,000 degrees Celsius, enough to melt silicate crust into global magma oceans. Rock literally boils, producing a thin atmosphere of vaporized minerals that can flow toward the night side, condense, and fall back as mineral rain. Lava oceans, rock vapor skies, and nightside surfaces that may be cold enough to refreeze the very rock that just boiled away. No one expects a rocky planet to behave like this. The phrase sounds familiar, Earth-like, safe. But on worlds like 55 Cancri E, which circles its star in about 18 hours, rocky means oceans of molten basalt, a crushing gravity field, and perhaps a carbon-rich interior where, under titanic pressures, diamond could form deep below the surface. By the end of tonight, you're going to understand that these regimes of heat and gravity push solid matter into phases rarely seen outside high-energy laboratories. Their existence is a direct challenge to models of how planets migrate and survive. Standard formation theories place rocky planets farther out, then allow some to spiral inward. Yet many ultra-short period super-Earths sit so close that tidal forces should slowly drag them into their stars. The clock is ticking, but the exact timescale is a puzzle, and absolutely no one anticipates the diversity of densities now being measured. Because these planets transit, spacecraft can weigh them with exquisite precision using transits and radial velocities. Some come out iron-rich, denser than Earth, hinting at stripped mantles or giant metallic cores. Others look closer to Earth like mixtures of rock and metal. A few are so low density or so compact, that they may represent completely new categories of planetary composition. Now, let's begin to think of rocky as a spectrum, not a promise. These worlds prove that beyond our solar system, solid surfaces can mean lava seas locked under eternal noon. In the next section, the story gets even stranger, as gravity itself starts tearing planets apart. Gravity can melt rock and lock a hemisphere into endless noon. But what about the skies above those lava seas? Tonight we're going to leave the ground and look up, into atmospheres that turn familiar materials into alien weather. Before we get started, remember where we already are in this mission through exoplanet space. There are hints of silicate clouds that could fling molten glass sideways in the wind, metal vapors boiling off ultra-hot gas giants, even rock vapor atmospheres on worlds so close to their stars that the crust itself is evaporating. Now stretch that picture. Scientists have also discovered traces of sodium, potassium, water vapor, carbon monoxide, and mysterious hazes that may be built from complex hydrocarbons, hanging high like smog on a planetary scale. Those sodium and potassium fingerprints were the first atmospheric signatures ever seen beyond our solar system. As a planet like HD 29458b passed in front of its star, the starlight dimmed at very specific colours. The pattern was unmistakable. Atoms of sodium and potassium were absorbing light, proving that the planet carried a gaseous envelope. From that point on, the game changed. By the end of tonight, you're going to understand how a few dark lines in a spectrum can reveal entire alien skies. Follow-up observations with more sensitive instruments found water vapor and carbon monoxide on many hot Jupiters, and in some cases broad, featureless slopes in the spectrum that point to hazes. On worlds with methane and ultraviolet radiation, those hazes may be long chains of hydrocarbons, cousins of the compounds that give Titan its orange shroud. No one expects a simple, clear blue sky. Instead, the boundary between space and cloud can be thick, layered, and deeply coloured. Temperature is the architect here. On cooler gas giants far from their suns, clouds condense from familiar materials: ammonia ice, water ice, maybe ammonium hydrosulfide. Move inward, and the thermostat climbs. On hotter giants like WASP 76b, iron can vaporize on the day side and then condense as droplets on the cooler night side, leading to the famous idea of iron rain. Push the heat even further, and minerals such as corundum, the crystal form behind sapphires and rubies, or silicates can form cloud decks, turning the upper atmosphere into a suspension of microscopic gemstones and glass. Composition and stellar irradiation decide which substances freeze out at which heights. The result is a stack of cloud layers, each made from a different mineral, each forming at a different pressure and temperature. Where Earth has water clouds at a few altitudes, an ultra-hot Jupiter might have corundum clouds high up, silicate clouds lower down, and deeper still, a metal-rich haze where the gas begins to glow. Picture standing on a hypothetical solid platform in that environment, looking up. The clouds above are not soft vapour but blizzards of corundum crystals or glassy grains, glinting in a dim, copper-coloured light. The sky might fade from black space to a glowing mineral fog, with lightning crackling through clouds made of a rock. And beneath your feet the surface could be just as extreme, an endless ocean of lava like 55 Cancri E, or a carbon world whose crust hides layers of diamond compressed under titanic pressure. No one predicts that a sky of gemstones and a ground of molten rock will be the quiet part of the story. In the next section, the violence intensifies, as tides and radiation begin to rip whole planets apart. Lava seas and diamond crusts are violent, but the strangest twist comes when the fire goes out and everything turns to water. Tonight we're going to dive into worlds that drown their continents, where the calm blue surface hides an alien interior that no ocean on Earth can match. On Earth, oceans are a thin film, an average depth of a few kilometers, puddled on top of a rocky surface with mountains, continents, and a direct rock-water boundary. A water world flips that picture. Imagine a planet where a significant fraction of its entire mass is H2O, not just a surface layer. Global oceans not 5 or 10 kilometers deep but 500. No beaches, no continents, just an endless, horizon-to-horizon sea wrapped around the whole planet. At first, that sounds almost familiar. A wetter Earth. But push that much water under gravity, and pressure does something unexpected. At the bottom of a super ocean, hundreds of kilometers down, the weight above can reach gigapascals. Under those conditions, water does not behave the way intuition says it should. It can freeze into exotic high-pressure ices, ice Ver, 7 and beyond, while the layers above remain liquid and mobile. The result is a structure no one predicts from looking at the surface. A deep liquid ocean, then a solid mantle of high-pressure ice, and only below that, a rocky core. Earth's seafloor sits right on its rock, allowing direct interaction between water, crust, and mantle. On a true water world, that interface is hidden. The ocean never directly touches stone. Scientists infer candidates for these drowned planets from a simple but powerful clue: density. Measure a world's mass and radius, place it on the radius-mass diagram, and some objects fall far below the line for pure rock or rock plus a thin atmosphere. Too light for their size, too puffy to be made only of iron and silicate. Worlds like Kepler-22b, some of the TRAPPIST-1 planets, and several mini-Neptunes hint at large water fractions, perhaps deep global oceans extending far beyond anything in the solar system. But there is a catch. Without detailed atmospheric measurements, those compositions remain uncertain. A low density could mean a thick hydrogen-helium envelope, a steam-rich atmosphere, or a true water mantle. The data draw a boundary of possibilities. The exact interior is still hidden. By the end of tonight, you're going to understand that even with powerful space telescopes and sensitive instruments, some of the most important layers stay out of reach. If the interior is water-rich, everything about the planet's geochemistry and climate regulation changes. On Earth, plate tectonics and land-based weathering pull carbon from the atmosphere and lock it into rocks. Rivers carry nutrients from continents to the sea. On a super-ocean world with no exposed land, that cycle breaks. Limited weathering. Perhaps sluggish exchange between the rocky core and the ocean, choked by that high-pressure ice mantle. Life, if it emerges, would have to adapt to a different playbook. Maybe it thrives in endless sunlit surface waters, under a gentle sky and a stable climate moderated by the sheer heat capacity of a global ocean. Or perhaps the real action happens deep below, near hydrothermal vents buried under kilometers of high-pressure ice, where fractures and pockets allow chemical nutrients to leak upward in slow, persistent plumes. From far away, these planets would look deceptively simple, a small pale dot. No continents, no visible storms like Jupiter's Great Red Spot. But beneath that quiet face, pressure, ice, and water carve an interior as layered and complex as any molten super-Earth. No one expects that the most Earth-like looking worlds could host the most alien oceans. Before we get started with tides tearing planets apart, hold that image of a silent blue sphere in mind. Because in the next section, those same forces that stir super-oceans will be pushed to extremes, until gravity itself starts shredding worlds into rings and streams of planetary debris. Now, let's begin. Those same tides that can shred a planet into rings are only half the story. The other half is invisible. Magnetic fields, radiation belts, and a stellar wind that can turn an entire solar system into a storm zone. Tonight, we're going to step into that storm. Many of the most bizarre exoplanets discovered so far huddle close to their stars, where the stellar wind is not a gentle breeze but a blast furnace of charged particles. Flares and coronal mass ejections erupt with energies far beyond the worst solar storms in recorded history, and they don't arrive once a century. They can hit weekly, sometimes daily. Near an ultra-hot Jupiter like WASP-76b or Kelt 9b, the star's magnetic field lines sweep past at hundreds of kilometers per second, whipping the planetary atmosphere. The expectation is a calm, stratified sky. The reality is a boiling, electrically charged plasma, constantly stirred, constantly shocked. No one predicts that space weather would become as important to exoplanet science as temperature or mass, but that's exactly what is happening. If a planet carries its own magnetic field, the story changes again. That field can carve out a protective bubble in the stellar wind, forcing particles to spiral along invisible lines and pile up in radiation belts. Around Earth, those belts are dangerous but manageable. Around a close-in giant, models suggest belts so intense that a spacecraft passing through would be fried in seconds. The same trapped particles can drive auroras far brighter than anything at our poles, turning entire hemispheres into curtains of high-energy light. By the end of tonight, You're going to understand why those fields matter for survival. Magnetic shielding slows the erosion of atmospheres, deflecting a fraction of the incoming wind and high-energy particles. Without it, the upper atmosphere can be sandblasted away, molecule by molecule over billions of years. Pattern interrupt. Imagine turning off the star. Some rogue planets drifting between the stars may still carry internal magnetic fields, their invisible shields glowing with ghostly auroras powered not by a sun, but by cosmic rays and the galactic environment beyond any familiar boundary. Now place the star back and make it small and red. Red dwarf stars, the most common hosts of Earth-sized planets, often behave like cosmic flamethrowers. They unleash powerful UV flares and particle storms that can bathe nearby worlds in radiation doses that would sterilize an unprotected surface, stripping atmospheres and oceans unless gravity and magnetism fight back. Astronomers have actually seen the scars of this battle. Some close-in planets are wrapped in vast hydrogen halos, detected as they transit and absorb starlight. Those halos are planetary atmospheres in the act of escaping, torn away by heat and wind. Simulations show that habitability around these stars is not a simple yes or no, but a moving target in time, depending on how quickly the star calms down and how long the planet can hold on. So picture an alien sky under these conditions. Constant, violent auroras racing from horizon to horizon. A star that brightens and darkens in brutal flashes. Lightning in the upper atmosphere as charged particles slam into gas. No one expects calm blue noon. Absolutely no one anticipates a gentle night. And that brings up a larger question. In a galaxy filled with such magnetic chaos, such extreme space weather, how unusual is our quiet, relatively stable solar system really? In a galaxy filled with magnetic chaos and brutal space weather, our quiet neighborhood starts to look suspicious. When scientists line up the catalogue of worlds discovered so far against the 8 planets of the solar system, a strange question appears at the boundary of our understanding. Are those bizarre exoplanets the odd ones out, or are we? Now, let's begin. Think back through the planets visited so far in this mission. Ultra-hot Jupiters like WASP-76b, with vaporized metals and possible iron rain. Lava worlds like 55 Cancri, where an ocean of molten rock may stretch from horizon to horizon. Carbon planets that could hide layers of diamond under crushing pressure. Rogue planets drifting alone through interstellar space. Compact systems like TRAPPIST-1, with 7 Earth-sized planets crammed closer than Mercury's orbit. Deep water worlds that might be wrapped in global oceans hundreds of kilometers thick. How many direct analogues exist in our solar system? Almost none. There is no hot Jupiter hugging the sun with a 2-day year. No super-Earth skimming just beyond Mercury, glowing red with tidal heat. No known global ocean planet with thousands of kilometers of water. Instead, the system is spread out, with small rocky planets inside, gas and ice giants outside, and nothing in between. That architecture feels natural because it is home. But in the exoplanet census, it is not typical. Surveys like Kepler and TESS showed this with brutal clarity. When those spacecraft stared at thousands of stars, the most common planets discovered were not Earth twins or Jupiter clones. They were close-in super-Earths and mini-Neptunes, worlds 2 to 4 times Earth's size, often orbiting in just a few days or weeks. By the end of tonight, you're going to understand how strange it is that the solar system has none of them. Hot Jupiters turned out not to be the dominant population, but they are far from rare, and yet there is no giant planet broiling in a 4-day orbit around the Sun. Why? One hypothesis points to Jupiter itself. In some models, Jupiter forms early and migrates inward, then back out, ploughing through the inner disk like a gravitational snowplow. Planet embryos are scattered, accretion is disrupted, and any forming super-Earth chain near the Sun is cleared out. Our particular formation environment, the mass and temperature of the protoplanetary disk, even the timing of when the solar wind ignited may all have been unusual compared to the average planetary nursery. There is a catch. The detection methods used so far are biased. Transit surveys favour big planets close to their stars. Radial velocity favours massive worlds on tight orbits. No one expects a survey like that to give a fair sample of every possible architecture. And absolutely no one anticipates that the first few thousand planets discovered will tell the whole story. Even after correcting for those biases, though, the solar system still looks slightly off pattern. No inner super-Earths, no hot Jupiter, wide separations between planets. So Earth and its neighbours stop being the default template and become one peculiar outcome among many. A system with long-term stability, moderate orbits, and a temperate, persistent habitable zone is not guaranteed. It is one roll of the cosmic dice. That makes this calm blue noon, this gentle night sky, feel more precious and more precarious, and it raises a deeper problem. If typical planetary systems look nothing like ours, what does that do to the search for other Earths? If planetary systems like ours are just one roll of the cosmic dice, then the old rulebook for planets shatters almost instantly. The classic categories that every textbook leans on, terrestrial, gas giant, ice giant, were all reverse engineered from a single sample, our solar system. They work beautifully here. Rocky worlds in close, gas giants in the middle, ice giants on the edge. Clean, ordered, predictable. But the moment spacecraft and telescopes began to detect planets beyond this neat arrangement, the scheme collapsed. Ultra-hot Jupiters hugging their stars in 2-day orbits, temperate super-Earths with no analogue in our system, warm Neptunes puffed up by stellar radiation. No one expects the first 1,000 exoplanets to fit into 3 tidy bins, so scientists did something very human. They started naming the chaos. Tonight, we're going to watch classification turn from a filing system into a survival tool. Now let's begin. The new schemes do not start with rocky or gassy. They start with numbers, radius, mass, equilibrium temperature, incident flux, the raw power of starlight beating down on a world. Combine those, and new regimes emerge. Ultra-hot Jupiters, with daysides hot enough to vaporize metals and drive fierce atmospheric winds. Warm Neptunes, mid-sized planets where hydrogen envelopes and icy interiors wrestle for dominance. Temperate super-Earths, in that fragile zone where liquid water might exist, but surface conditions could range from ocean paradise to global magma sea. Prediction meets observation, and the surprises keep escalating. Plot planet radius against orbital period, and a strange gap appears, a missing band between about 1.5 and 2 Earth radii. Above the gap, mini Neptunes with thick atmospheres. Below it, compact super-Earths with stripped skies. That radius valley is a transition zone, a fossil imprint of atmospheric loss and interior composition. Some planets start puffy and evaporate under relentless stellar wind and radiation. Others form dense and never inflate. No one predicts that such a sharp boundary would carve the exoplanet population in two, yet there it is, written in the data. Those transition zones are not just curiosities. They are checkpoints for planetary evolution models. If a theory cannot reproduce the valley, the ultra-hot Jupiter regimes, the warm Neptune desert, it fails. By the end of tonight, you're going to understand that every bizarre outlier, every WASP-76b with possible iron rain, every lava-locked 55 Cancri E is a stress test on our physics. And this is only the beginning. As better instruments dissect exoplanet atmospheres, future taxonomies may pivot from bulk properties to chemistry. Worlds grouped not just by size, but by cloud decks and condensates. Silicate cloud giants where rock vapor forms high-altitude hazes. Water-rich sub-Neptunes wrapped in deep steam envelopes. Carbon-dominated tar worlds, smoggy and dark. Absolutely no one anticipates a periodic table of planets, yet that is where the mission is heading. The question is, once planets are sorted by the very air they breathe, what new category will the strangest worlds force us to invent next? Those strange new categories aren't just labels. They are pressure points on our theories. Each time a world refuses to fit, the entire story of how planets form, migrate, and age has to be rewritten. Before we get started, remember what the standard solar system used to look like in the textbooks. Small rocky planets close in, giant planets far away, quietly orbiting in neat circular paths. Then hot Jupiters were discovered, skimming their stars every few days. No one expects a Jupiter tucked closer than Mercury. No one predicts a gas giant like WASP-12b, stretched by tides and broiling at thousands of degrees. The only way to make sense of them is to let giant planets move. So planetary formation models changed. Tonight, we're going to watch those models grow teeth. In the new picture, a Jupiter can form far from its star, then spiral inward through the gas disk, ploughing through dust like a snowplow in space. Or it can be kicked onto an eccentric path by another giant, then have its orbit shrunk and circularized by tides, large-scale migration, disk torques, gravitational scattering. Suddenly the quiet solar system becomes a dynamic, rearranging machine. Then come the super-Earths and mini-Neptunes. Planets between Earth and Neptune in size a range our own system completely skips. Some, like 55 Cancri e, sit so close to their stars that rock melts into global lava oceans. Others carry thick hydrogen and helium envelopes, more like shrunken Neptunes. Prediction versus observation again. Early models expected either small rocky worlds or big gas giants, with little in between. Instead, scientists discovered that disks can build a continuous spectrum. Whether a planet keeps its gas or is stripped to a bare core depends on disk mass composition, stellar wind, and the violence of early flares. Orbit shapes add another twist. Many exoplanets follow stretched, tilted, even backwards paths relative to their star's spin. That demands drama. Planet-planet scattering hurls worlds into new configurations. Kozai lid-off cycles with a distant companion slowly pump eccentricity, trading inclination for elongated orbits until tides take over. One close encounter, one missed collision, and an entire system is reshaped. Then the pattern interrupt. Rogue planets, worlds like Ogle 2016, BLG 1928, drifting between the stars with no sun at all. They are the fossils of gravitational chaos, flung completely out of their birth systems. These bizarre planets act as boundary conditions for theory. If a model cannot produce ultra-hot Jupiters, lava worlds, and rogue planets in the right proportions, it is incomplete or wrong. By the end of tonight, you're going to understand that we are not collecting trivia. Each extreme world is a data point. Together, they tell us how often the chaos of formation settles into something calm and stable, something like our own life-friendly system, and how often it does not. Now, let's begin the final step, putting all of these alien systems into one cosmic context. All of these alien systems point to one unsettling conclusion. The old idea of a narrow Goldilocks band around a star is no longer enough. The classical habitable zone was a clean circle on a diagram. The real galaxy is not that polite. Tonight we're going to stretch the word habitable until it almost snaps. Rogue planets drifting in the dark, tidally locked infernos like WASP-76b, global ocean worlds, and even the high-altitude layers of hotter planets all hint at plausible niches for life. The familiar ring around a star becomes only a starting point, a first guess rather than a hard boundary. On Earth, life has already rehearsed for many of these extremes. It thrives at deep-sea vents where sunlight never reaches, feeding on chemical energy from the interior rather than the sun. It persists in acidic hot springs that would dissolve metal, and in high radiation zones around nuclear disasters where almost no one expects survival. Prediction versus observation again. Textbooks once placed tight limits on habitability. Microbes quietly ignored them. Those examples push scientists to take more exotic exoplanet habitats seriously. If bacteria can endure scalding acid pools, why not subsurface oceans beneath the ice of a rogue planet, warmed by radioactive decay and tidal flexing? If spores can ride high in Earth's atmosphere, why not microbial layers floating in the temperate altitudes of a superheated giant, far above the molten clouds and glass rain? The mission now is to understand not just where liquid water might exist on the surface, but where energy and chemistry can persist in 3 dimensions, from core to sky. At the same time, some worlds sketch the outer walls of possibility. Ultra-hot Jupiters like Kelt 9b, with atmospheres heated above 4,000 degrees Celsius, strip metals into vapor and bleed mass into space. Lava planets such as 55 Cancri e, potentially with diamond-rich interiors and oceans of molten rock circle their stars in hours. These are almost certainly too hostile for life as we know it. Yet their very hostility is useful. They define the edges of planetary conditions, framing the parameter space where life might still find a foothold and where it almost certainly cannot. Before we get started on the search for life itself, the tools for that search are already in development. Spacecraft and telescopes are being tuned to read exoplanet atmospheres as if they were forensic reports. Oxygen paired with methane, or other gas combinations that should not coexist in chemical equilibrium. Bizarre planets become control cases. If an ultra-hot Jupiter shows oxygen without biology, or a glass rain world shows methane from geology alone, Scientists learn what false positives look like before declaring a distant sunrise alive. So in a galaxy where planets rain glass sideways, drift starless through interstellar space, and may hide diamond cores under global magma seas, what forms might life take if it emerges under such alien rules? And how would anyone even recognize it when the signal finally arrives from beyond our solar system? To even recognize that signal from beyond our solar system, the next step is clear. The eyes themselves have to change. Tonight we're going to stand behind those new eyes. The James Webb Space Telescope is already rewriting what the word planet means. Designed as a general-purpose observatory, it has quietly become an exoplanet machine, spreading starlight into rainbows so detailed that scientists can read the fingerprints of alien skies, water vapor on hot Jupiters, carbon dioxide on compact sub-Neptunes, clouds, hazes, and temperature structures on worlds so scorched that rock may vaporize into the wind. Expectation, a blur of light. Reality, layered atmospheres, mapped in transmission as planets cross their stars, and in emission as their glowing daysides rotate into view. With Webb, ultra-hot Jupiters like WASP-76b stop being distant points and become weather experiments where metal may condense and fall as iron rain on the night side. Sub-Neptunes that once looked like featureless mini-Neptunes now reveal whether they're wrapped in hydrogen, choked with steam, or hiding high-altitude clouds that flatten their spectra. By the end of tonight, you're going to understand that this is only the warm-up, because Webb is not alone. The Nancy Grace Roman Space Telescope will turn the sky into a statistical survey, a mission built to capture thousands of planetary systems at once. Its wide-field vision and coronagraph will block out blinding starlight, letting faint reflected light from giant planets emerge from the glare. Ariel, the atmospheric remote sensing infrared exoplanet large survey, will go further, dedicating nearly its entire mission to one question. What are exoplanet atmospheres really made of, across every wildly different class of world we've discovered so far? No one expects these observatories to look only for Earth twins. They are designed to catalogue the full zoo. Lava worlds like 55 Cancri E, bloated hot Jupiters, temperate sub-Neptunes, frozen giants on stretched orbits, and planets that defy our current categories. With improved sensitivity and spectral resolution, tiny wiggles in a spectrum translate into subtle atmospheric components, traces of methane, metal hydrides, photochemical hazes that only form under brutal ultraviolet light. Future direct imaging concepts push the boundary even harder. Star shades flying tens of thousands of kilometers from a spacecraft. Giant segmented mirrors with coronagraphs tuned to suppress starlight by factors of 1 billion. No one predicts the first Earth-like planet image will be a postcard. It will be a faint changing dot. But brightness variations over time can hint at oceans, continents, even seasonal clouds, all inferred from how that dot reflects its star's light. As these tools come online, absolutely no one anticipates the current most bizarre exoplanets list will survive. The strangest worlds may be the ones that look boring at first glance, until their spectra whisper something impossible. Now, let's begin to ask, when the instruments finally show a planet that should not exist, what breaks first, the data or our understanding of how planets form at all? When a headline says iron rain or lava ocean, it sounds like pure science fiction. Tonight we're going to peel that back and show how those wild phrases are anchored to something very simple. Tiny, repeating dips in starlight and faint whispers of colour in space. By the end of tonight you're going to understand how those dips become maps, how those maps become climates, and how those climates become the alien landscapes playing in your imagination. Start with a transit. A planet crosses its star, and the star's light drops by a fraction of 1%. From that alone, scientists extract the planet's size. A deeper dip means a larger planet blocking more of the solar disk. Expectation, just a silhouette. Reality, the boundary of the planet is not sharp. Some starlight filters through a thin atmospheric shell, leaving fingerprints in the spectrum. Measure that dip at different wavelengths, and something new appears. If the planet looks slightly bigger in blue light than in red, that suggests a puffy, gas-rich envelope scattering shorter wavelengths, more like a mini Neptune than a dense rocky super-Earth. If the transit depth barely changes with colour, the world may be compact, with either a thin atmosphere or high-altitude clouds muting the signal. This is how WASP-76b reveals vaporized metals, while other planets hint at clearer, drier skies. But the story doesn't stop at the edge of the disk. As a planet orbits, its illuminated hemisphere rotates into and out of view, and the combined light of star plus planet rises and falls in a repeating pattern called a phase curve. For ultra-hot Jupiters, those curves show the day side glowing like a small ember beside the star, then fading as the night side rotates toward us. The peak doesn't always line up exactly with noon on the planet, which means fierce winds are hauling heat eastward, shifting hotspots and carving dramatic day-night temperature contrasts. In a few extreme cases, subtle wiggles in the phase curve even betray cloud patterns, bright reflective regions marching around the planet or dark, clear zones where the deep atmosphere radiates freely into space. Then there is mass. Radial velocity measurements track the star's tiny wobble, as an unseen companion tugs it back and forth. Combine that wobble with the planet's size from transits, and density emerges. High density points to iron and rock. Low density screams hydrogen, helium, and ices. No one expects a world with Earth's radius but cotton candy density to be a solid surface. No one predicts a Jupiter-sized planet with near-stellar temperatures to keep all its gases forever. Here is the pattern interrupt. Those beautiful spectra and curves are not pictures. They are inputs to atmospheric retrieval codes, statistical engines that test millions of combinations of gases, clouds, and temperatures. Each combination generates a synthetic spectrum. The algorithms compare those to the real data, over and over, until the most likely family of atmospheres rises out of the noise, with uncertainties attached. So when a mission reports iron rain on WASP-76b or lava oceans on 55 Cancri E, it means the temperatures, pressures, and compositions implied by the light leave very few alternatives. The language is dramatic, but the logic is conservative. These spacecraft are not guessing. They're reading the wind and weather of planets light years beyond our solar system, all from the faintest changes in a star's glow. Now, let's begin to ask what happens when those same techniques are turned on quieter targets. Small, cool worlds where the most shocking discovery would be something utterly familiar. Those quieter targets are not quiet at all. They are loud in other ways. Heat, gravity, chemistry pushed to the edge. Before we get started on the final verdict about what these worlds mean, pause and imagine something more personal. Tonight, we're going to hand you an indestructible spacesuit and a one-day ticket to anywhere beyond the solar system. No life support limits, no radiation worries. One day on a world that no one expects could even exist. Picture stepping out into the furnace of WASP-76b. On the day side, the atmosphere is hot enough to vaporize metal, so hot the very air peels apart under the star's glare. Winds whip that metallic vapor around the planet, and on the cooler night side it may condense and fall as iron rain. Not gentle droplets, sheets of glowing metal, slashing down through a sky lit by a permanent distant sunrise. Or choose 55 Cancri a super-Earth that whips around its star in less than 18 hours, locked, so one face is in unending day. Beneath your boots, an ocean of lava could stretch to every horizon, black crust cracking to reveal orange rivers. Deep below, under pressures that crush language, a carbon-rich interior might be forging literal diamond. Walking there would be like crossing the exposed heart of a planet in mid-formation. Maybe the ticket takes you to a rogue planet, a world flung out of its system, drifting alone through interstellar space. There is no sunrise here, no sunset, just eternal night. You stand on frozen ground under a sky of unmoving stars, the Milky Way hanging like a bright scar across the dark. The only weather is the slow fall of micrometeorites and the distant whisper of the galactic wind. Or you could aim for a TRAPPIST-1 world where the star is small and dim but hangs huge in the sky. The planet may be tidally locked, one side roasting, one side frozen. You walk along the Terminator, the narrow band of perpetual twilight where day and night wrestle to a draw. On one horizon, a deep red sun hovers forever. On the other, stars are already visible, and neighbouring planets might glow as bright as our moon. By the end of tonight, you're going to understand that this choice is not just a thought experiment. It is a vote. Which impossible world would you visit, and why? Iron rain on WASP-76b, lava and diamond depths on 55 Cancri E, the silent dark of a rogue planet, or the endless sunset of TRAPPIST-1's twilight line. Describe the scene you would seek out, walking that knife edge between day and night, watching glass rain streak sideways in a superheated storm, or standing in the dark while the constellations never rise or set. Those responses do more than feed curiosity. They steer the mission. Comments and discussion help decide which planet earns a full deep dive episode, a narrative journey that turns your chosen world into the next destination for this series. No one predicts how powerful that collective focus can be. Absolutely no one anticipates which world will win. Now, let's begin to pull the camera back, because whichever ticket you choose, the simple fact that these planets exist at all is a profound statement about the creativity of physics, the wild diversity of planetary systems, and how much more space is waiting beyond every boundary scientists thought they understood. That creativity of physics is the real headline. Ultra-hot Jupiters with vaporized metals, lava worlds skimming their stars, rogue planets drifting in the dark between suns. Each one is a quiet revolution in how scientists think planets are born, move, and survive. Before we get started on the emotional ending, this is the moment to take stock, because every class of bizarre world has kicked over a different part of the old solar system rulebook. Hot Jupiters like WASP-76b and Kelt-9b showed that giant planets do not have to live in the cold outskirts. They can migrate inward, ride the solar wind of their parent stars, and park on orbits so tight that metals vaporize and may rain out on the night side. No one expects that when the only template is Jupiter. Lava worlds and carbon planets push the next boundary. Worlds like 55 Cancri E, orbiting in less than a day, forced models to include rock that behaves almost like a fluid, mantles that can be half molten, and interiors where carbon can compress into diamond. Water worlds and compact systems like TRAPPIST-1 showed that entire planetary systems can be squeezed closer to a star than Mercury is to the Sun, with extreme tides, synchronized rotations, and perhaps global oceans instead of scattered seas. Rogue planets did something even stranger. They reminded everyone that planets are not just accessories to stars. Some are flung out during violent early reshuffling, crossing interstellar space alone. Detected as brief gravitational lenses, they prove that planet formation and ejection are more chaotic than any neat diagram suggests. The result is a new picture where diversity is not the exception, diversity is the rule. By the end of tonight, you're going to understand that the key lesson is not simply, the universe is weird. The key lesson is that early assumptions, drawn from a single, quiet, middle-aged solar system, were deeply incomplete. Earth is no longer the generic Earth-like planet in a textbook sketch. It is one specific point in a vast parameter space, with a rare combination of long-term stability, moderate climate, and a star that has not yet torn its worlds apart. These strange planets are not just curiosities. They are natural experiments in extreme physics. Ultra-hot Jupiters test theories of atmospheric chemistry at thousands of degrees. Lava worlds and tidally stressed super-Earths probe how rock, metal, and even diamond behave at crushing pressures. Water worlds and compact systems reveal how tides, magnetic fields, and stellar wind sculpt atmospheres over billions of years. Tonight we're going to treat them as what they really are, laboratories scattered across the galaxy. Because of them, planets are no longer abstract points of light on a plot. They are places, with weather, with geology, with histories, and the most unsettling realization is still ahead, hiding in what these worlds imply about life, and about how ordinary, or extraordinary, your own world might be. So now, pull back, not just from these individual planets, but from your room, from your street, from your whole world. Tonight, we're going to zoom out until your familiar solar system shrinks to a tiny circle of light, just one arrangement of planets among hundreds of billions of stars, each one a potential stage for storms and oceans and geology that no one predicts in advance. Before we get started on what that really means, anchor in one simple contrast. A few decades ago, scientists knew exactly 0 planets beyond the Sun. 0. Theories were neat, the diagrams tidy, the solar system presented as a kind of template. Now, the catalogue holds thousands of confirmed exoplanets and tens of thousands of candidates, and the neat diagrams have exploded into a wild zoo of worlds that absolutely no one anticipates. The speed of that transformation is almost violent. In the early 1990s, a single hot Jupiter upended models of planet formation. Then came ultra-hot Jupiters like WASP 76b, where the day side is hot enough to vaporize metals, and the night side may see iron condense and fall as iron rain. Then came 55 Cancri E, racing around its star in under 18 hours, with a carbon-rich interior that could forge diamond deep below a global magma ocean. Each mission, each new spacecraft, doesn't just add a data point. It tears out pages of textbooks and forces the system of ideas to rebuild. This is the new humility. The solar system is not the master plan. It is one local solution to the physics of gas, rock, ice, and time. For every Earth, there may be a rogue planet like Ogle 2016 BLG 1928, drifting through interstellar space with no star, wrapped in eternal night. For every calm blue sky, there is a world with horizontal glass rain, driven by winds of thousands of miles per hour, or a planet whose day side glows hotter than some stars, while the night side lurks in near-frozen darkness. Pattern interrupt. Pause on that mental image. Somewhere, right now, as this sentence reaches you, there are real storms of molten glass. There are nights when iron falls from alien clouds. There are lava oceans on tidally locked super-Earths, and compact systems like TRAPPIST-1 where 7 Earth-sized planets crowd so close to their star that tides can rip open their crusts. By the end of tonight, you're going to understand that these are not science fiction backdrops. They are active experiments in climate, chemistry, and geology, running in parallel across the galaxy, and this loops back to you. The next time you look up, the night sky is no longer a flat backdrop of anonymous points. It becomes a 3-dimensional map of planetary laboratories, each star a possible host to winds, oceans, and boundaries pushed to extremes. Your own world stops feeling like the default and starts feeling like one fragile, improbable outcome among countless strange worlds still waiting to be discovered, and perhaps, one day, visited. That shift in perspective is the beginning of a new mental map of the cosmos. Tonight, we're going to turn that feeling of wow, there are so many weird planets into a framework you can actually use every time a new world is announced. Before we get started, erase the old 2-box model in your head. Not just like Earth, or like Jupiter. The real space of planets is multidimensional: size, composition, temperature, orbit, stellar environment. Each axis stretches from familiar to extreme, and the most bizarre worlds live where those axes intersect in ways absolutely no one anticipates. Take temperature and orbit. Ultra-hot Jupiters like Kelt 9b and WASP 76c hug their stars so closely that their atmospheres reach thousands of degrees. Metals vaporize. On WASP 76b, scientists see signatures of iron in the air, hinting at iron rain on the night side. Same basic category as Jupiter, but placed deep into the close-orbit high-temperature corner of your map, it becomes a different kind of object entirely. Shift along composition, and you hit carbon worlds like 55 Cancri E. Similar in size to a super-Earth, but circling its star in less than a day, with pressures that might forge diamond deep inside. Slide toward isolation, and the map takes you beyond stars altogether, to rogue planets like Ogle 2016 BLG 1928, detected only when their gravity briefly bends the light of a background star. Same physics of mass and gravity, completely different region of the landscape. By the end of tonight, you're going to understand how to use that landscape. The next time a mission reports a new discovery, you can ask, is this a lava world hugging its star? A bloated, ultra-hot Jupiter losing atmosphere to stellar wind? A compact water world? A frozen giant? A rogue planet? Or something that forces a brand new category? Instead of a random zoo, your brain starts placing pins on a chart. Now, let's begin to layer in how these worlds are actually found. Transits favor large planets close to their stars. Radial velocity likes massive companions tugging hard on their suns. Microlensing catches brief alignments, making it one of the only ways rogue planets appear at all. The current catalogue is not a neutral census. It is a biased snapshot shaped by our instruments, our angles, and our patience. No one predicts that this bias will last forever. As new space telescopes launch and longer baseline surveys accumulate, the map fills in. Patterns emerge. Hot Jupiters hint at migration through the solar system they inhabit. Escaping atmospheres sketch invisible boundaries between safe orbits and destructive radiation. Tidal forces in systems like TRAPPIST-1 sculpt lava oceans and possible subsurface seas. Feeling overwhelmed by the diversity is normal, but when you zoom out and watch those patterns — migration, atmospheric escape, tides — you see planetary evolution, not chaos. You become part of a small but growing group of people who can hear a headline about some newly discovered glass-raining world and immediately grasp what is at stake. And in the final moments of this mission through strange planets, that perspective is exactly what will matter most. You have just crossed a strange kind of boundary. From glass rain and iron storms to rogue planets drifting through interstellar space, to diamond interiors locked under crushing pressure, you stayed with this mission from launch to distant orbit. That time and attention are not trivial. They are the fuel that turned a list of exotic names into a mental map of real, alien worlds. Think about what your brain now holds. WASP 76b is no longer just a headline. It is a tidally locked furnace where vaporized iron may condense and fall as metal rain. 55. Cancri is not just a number. It is a super-Earth, where a carbon-rich interior could compress into diamond. Rogue worlds detected only as brief gravitational flickers are no longer abstract. They are planets wandering beyond any solar system, sailing through the galactic wind in perpetual night. And while this episode pauses here, the science does not. Exoplanet discoveries are arriving almost weekly. No one expects the catalogue to slow down. No one predicts that the next few years will be boring. New telescopes, new instruments, and new algorithms are turning cryptic dips in starlight and tiny distortions in images into entire planetary systems, each stranger than the last. So tonight, somewhere out there in the dark, those impossible worlds are still spinning. WASP 76b is still raining vaporized iron sideways across its night side. HD 897733b is still flinging molten glass through winds faster than any sound on Earth. 55 Cancri E is still compressing its carbon-rich interior under pressures that may have crystallized diamond at its core. Ogle 2016 BLG 1928 is still drifting through interstellar space with no star at all, no sunrise to wait for, just endless night and the slow movement of distant constellations. There is something steadying in knowing that the universe makes worlds this strange. Every word of every textbook that called the solar system the default arrangement of planets was written before the first exoplanet was even confirmed. In a single human lifetime, the picture changed from 9 familiar worlds in one quiet system to a galaxy of glass storms and rogue planets and diamond crusts and lava oceans. The boundary of what a planet is allowed to be did not move a little. It exploded outward, and somewhere out there, the next strange world is already orbiting a star nobody has named yet. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.